Automated border control and airport security rely on facial verification systems that can process identity with high stakes and high speed. At a global entry kiosk, the operational requirement is to match a live camera feed against a stored database photo in a fraction of a second. The most naive mathematical approach involves a one-to-one pixel comparison between the two images. Pixel comparisons fail. With different lighting, RGB values for the exact same forehead pixel show massive mathematical variance. Shift the face 3 pixels left, and the coordinate map breaks entirely. Every pixel misaligns, despite the identity remaining identical. To a raw algorithm, a face is simply a matrix of light intensities. Pixels lack the semantic information necessary to understand identity. Modern computer vision addresses this by using an encoder network to perform end-to-end feature learning. The encoder network successfully maps the sheer complexity of a photograph into a single mathematical point, called an embedding. An embedding is a high-dimensional vector, often containing 128 distinct numbers. It serves as a specific coordinate within a vast mathematical void. In this coordinate plane, geographic distance represents semantic similarity. Here, 2 distinct photos of the same person land as vector points in close proximity. By setting a proximity threshold between these vectors, the system generates a match. An untrained neural network will plot these coordinates randomly. It has no innate understanding of which vectors should be neighbors. The central engineering challenge is designing a mathematical objective that forces the network to organize this latent space. In 2015, the FaceNet paper introduced triplet loss as a breakthrough method for teaching a network how to organize semantic concepts. This diagram illustrates the required data batching strategy. We pass 3 images into the network simultaneously: an anchor, a positive, and a negative. The anchor is the baseline. The positive is a different photo of the same person, and the negative is a photo of a completely different person. The images pass through the network and emerge as vectors in 3-dimensional latent space. This equation defines the learning objective. The network pulls the positive vector toward the anchor while repelling the negative vector. During training, the model updates its internal parameters specifically to satisfy this dual push and pull mandate. Triplet loss forces the network to discover facial features on its own. It learns to recognize identity without an engineer ever defining what a nose or an eye looks like. Triplet loss relies on heavily curated, human-labeled data to differentiate between positive and negative images. Manually sorting and verifying millions of photos into relational triplets requires massive time and financial resources. This reliance on human labor prevents the model from scaling to utilize datasets the size of the internet. Scaling further requires self-supervised learning, a paradigm shift that removes the human from the loop. Self-supervised learning extracts structure from the data itself. It allows researchers to train models on unorganized, internet-scale data. Engineers achieve this by tricking the network into generating its own triplets from unorganized chaos. Contrastive learning, via the SIM-CLAR framework, automates triplet generation. For the automation process, we start with an unlabeled dog photo, setting it as the anchor. A script duplicates and distorts it, rotating, cropping, adding noise, labeling this clone the positive. The negative is simply any random image from the batch, like a car. This creates the anchor positive-negative structure needed for the loss function without any manual human input. By running this process over billions of images, the network is forced to learn rotation and scale and variance to survive the loss function penalty. Replacing manual labels with algorithmic logic forces the model to build a robust and generalized understanding of visual reality. The principle of pulling pairs together and pushing random data apart applies beyond the visual domain. Weakly supervised learning utilizes naturally occurring data pairs found in the wild. Internet videos provide a primary source, as they contain naturally paired visual frames and audio tracks. This diagram plots a vector representing a video frame of a barking dog, alongside a separate vector for the audio of that bark in the same latent space. The loss function forces these vectors to occupy the same geographic coordinates. Cross-modal binding enables the network to understand that specific sound frequencies and pixel arrangements represent the same physical event. In the image-bind architecture, text acts as a central hub connecting diverse data types. This diagram shows text captions anchoring multimodal pairs. The text vector for dog creates a coordinate that audio and video vectors lock into. Shifting the text coordinate to drums makes the corresponding audio beat and drum set visual instantly align with it. This unified space creates emergent behavior, capabilities the model develops without explicit instruction. The model infers the relationship between the word drum, the sound of a beat, and the picture of the instrument, purely from the geometry of the embedding space. Modern artificial intelligence scales through the engineering of precise loss functions and data volume, letting the geometry of the latent space organize itself.